Like all machine learning algorithms, there is math that makes the decision tree possible. The good news is that the mathematics required for decision trees is quite straightforward. In this lesson, I will cover the basic math required for classification trees using the CART algorithm. In future lessons, we'll cover the mathematics of using the CART algorithm for regression trees. Trust me, you've got this if you want it. The math is not that difficult. And in fact, you might find that it's quite simple, and you might actually feel sorry for the computer because the computer has to do a lot of relatively simple calculations to make decision trees work. So let's go ahead and get started with the mathematics of impurity. As we know from a previous lesson, the objective of classification decision trees using the CART algorithm is to minimize impurity. So the easiest way to think about impurity is in a two-label or binary scenario. That's the easiest way to think about it. So we can use the adult census labels as our example. And in particular, we can think about a concept of a bucket of these labels. In addition, we also need to think of impurity as a spectrum, ranging from pure to impure and everything in between. Let's visualize what I mean by this concept of a bucket. As we can see here, I've got a little can, which represents my bucket. And you can see here, I have 4 instances of the less than or equal to $50,000 a year income label from the adult census data. And what we can see here is that all 4 are of the same kind, which means this is 100% of one of the labels. So this is pure. They are all the same value. They are pure insofar as all of these have the same label. Next up, we can think of another bucket over here with the greater than 50,000 a year in income label. And this is also pure because it's 100% of one label. Now we can expand this and think about a couple of other buckets where 3 out of the 4 are less than or equal to 50K, and 3 out of the 4 over here are greater than 50K. Because we have 75% of one label. It's kind of pure, but it's not as pure as these 2 buckets here because it's not 100% of one label. This is pure, this is a little less pure, this is pure, and this is a little less pure. And then lastly, we can think of the worst case scenario when we only have 2 labels. And that is the 50-50. This is as impure as you can get because this is more pure and this is more pure at 75%. So arguably and logically, 50% is the worst case scenario in terms of purity when you only have 2 labels. So using these buckets, we can define a conceptual spectrum that looks something like this, where we have pure at the ends and impure in the middle. Now remember, this is only for the 2 label case, the binary case, where we can say, hey, we go along the spectrum from pure for everybody that has incomes less than or equal to 50,000 a year. This is very pure. Everyone is in this bucket of all of these same values. And as we move the spectrum, we get more and more impure until we get to the worst case scenario, where half of the folks make more than 50,000 a year and half make 50,000 a year or less. And then we get back to pure again, where everyone's over 50,000 a year in income. So this is a spectrum. This is the intuition. The binary case is the easiest way to think about it, but generally speaking, this logic extends to if you have 3 labels, 4 labels, 5 labels, etc. But we're going to focus on the 2 label or binary scenario because it is the simplest to grok intuitively. And not surprisingly, if we want to create an algorithm that uses impurity to maximize the data splits, to make the best data splits in our classification tree, we need a calculation. The algorithm needs a calculation that embodies this spectrum to allow it to evaluate each split that's possible to say, hey, I'm looking for splits that are as pure as possible for the largest number of observations possible, or alternatively, I want to minimize the impurity for the splits for the most observations possible. This is our intuition, right? We have this spectrum of pure to impure in the binary case, and we need a calculation that allows us to understand what's going on with each potential split in the data so that the algorithm can pick the best split, the most optimal split. Turns out that there are several calculations several mathematical formulas that actually manifest the intuition that we saw on the previous slide. However, in this course, we're going to use the Gini impurity calculation. And the reason for this is because Gini impurity is widely used, and it is also the default calculation used in the R packages used in this course. Don't panic. We're going to take a look at a mathematical equation. Here it is. This is the calculation for Gini impurity. Don't worry about it. I know it looks fancy. We're going to go through it step by step, and it's going to be very intuitive. We're not going to necessarily focus on the mathematics per se, but we're going to take a look at the equation and understand what it means in terms of the logical processing that the equation implies. So first up, this big E-like thing, this is known as a sigma. You can interpret this essentially saying, hey, go through all the class labels. So you start at 1, that's what this means. Start at 1, and if you have C number of class labels, in our case, we're going to think of C being equal to 2 because we're dealing with the 2 label or the binary scenario. So C is equal to 2. Go look at class label 1, and then go to look at class label 2. So this says, look, just iterate through all the class labels. Now notice that even though we're dealing with a 2 label or binary scenario, this equation works if you have 3 labels, 4 labels, or 20 labels. It works exactly the same. That's the benefit of using this notation. It just says, look, no matter how many class labels you got, Dave, go through them all. Next up, this fancy thing right here in these square brackets just says, look, calculate the proportion of class labels. That's all it is. So let's say you have 3 labels of one kind out of 10 total labels. That proportion is 3 divided by 10, or 30%. Cool, no problem, right? Proportion, that's easy to calculate. And then next up, you take that proportion, whatever it is. In this hypothetical case, we said it was 3 out of 10, or 0.3, and we square it. And we just say, okay, take 0.3 times 0.3. Easy enough, that gives us 0.09. That's what all of this means right here. This is just a fancy way of saying, what is the proportion of the labels? Notice the I here, because the I represents, for example, class label 1. So what is the proportion of class label 1 at the particular node that you're talking about? That's what the T is for. And the next up, you say, okay, what does this mean over here? Hey, just take all of this gobbledygook to the right of the 1, and once you calculate it, just subtract it off. For example, we're using the 2 label binary scenario here. So we're going to do 2 calculations for the first class label and then for the second class label. And what we're going to do is we're going to say, okay, what is the proportion of the first class label in the node that we're looking at? Square that. Then go do it for the second class label. What is the proportion of class label 2 at the particular node? Find that out and square it. And then you subtract both of those values off of 1, and that gives you the final value. And once again, the T stands for any particular node in the tree. So the Gini for any node in the tree, denoted by T, is equal to 1 minus all this stuff over here. That's a little bit abstract. So the best way to actually learn this is just to walk through an example step by step. And that's exactly what we're going to do on the next slide. So this is super important. I'm going to repeat it again. As we know, the classification tree algorithm's objective is to minimize impurity. Reflexively, to maximize purity. There are 2 sides of the same coin. Now that we've got the math that we need, let's take a look at those buckets of labels that we saw a couple slides ago. Here you can see all of the buckets and our impurity spectrum. Pure and pure at the far ends and the most impure in the middle. Now that we have our buckets and our formula, let's go ahead and do the math. Trust me, you're going to find this surprisingly easy. Okay, let's take a look at this bucket over here on the left first. What we know from the previous slide is we need to calculate the proportions in our buckets, in our nodes, by class label. We can see that we have 4 labels, and all of them happen to be less than or equal to 50,000. So we can say 4 out of 4 of our labels are equal to less than or equal to 50K, and reflexively, 0 out of 4 are equal to greater than 50K because there are no greater than 50K labels in this bucket. So these are our proportions, 4 out of 4, 0 out of 4. So we can now plug and chug using that equation that we saw on the last slide. And here it is. So the Gini for this bucket is 1 minus, now all of this was that big letter E sigma thing and all that junk over there. That's what this is. But notice how simple it is. All it's telling you is, hey, go through all the class labels for your bucket, for your node, find out what the proportions are. And we already found those out pretty easily, 4 out of 4 and 0 out of 4. And we put the 4 out of 4 here and the 0 out of 4 here. We say, cool. Next up, the equation tells us we need to square these values. So we got a square and a square. Easy peasy, right? So if we plug and chug, we know that 4 out of 4 is equal to 1. And if we square that, 1 times 1 is equal to 1. Over here, we have 0 out of 4. That is equal to 0. 0 squared, or 0 times 0, is just 0. So we say, okay, take 1 minus 0, and that gives us a final Gini score of 0. Okay, that was a dramatic pause because hopefully you're seeing now that, wow, that fancy math we saw on the last slide ain't that difficult in practice. But just to really cement things, let's take a look at this node way over here on the right. We know that we have 0 out of 4 labels that are less than or equal to 50K, 0 out of 4. And we know 4 out of 4 of the labels in this bucket, in this node, are greater than 50K. And we can plug and chug. 0 out of 4 goes here, 4 out of 4 goes here, because we have 2 labels, because we're in the binary classification problem space. We square them, and that gives us 0, because 0 squared is 0, and 4 divided by 4 is 1, and 1 squared is equal to 1. And once again, we get a Gini value of 0. And this is super important. Notice that the Gini calculation is 0 when you have a pure bucket, a pure node of labels. This is awesome, right? Because if we're trying to minimize impurity, then that means that purity should be 0. That would be our objective, is to get something to be 0. And notice that this spectrum is awesome because the calculation shows 0 over here for purity and 0 over here. So if the algorithm minimizes the Gini calculation, either on the left side or on the right side, it doesn't really matter. As long as we get a Gini of 0 and a Gini of 0, that's what we really care about. Now let's look at the most impure node, this one right here in the middle. We know we've got 4 labels. Half of them are greater than 50K. Half of them are less than or equal to 50K. So 2 out of 4, 2 out of 4. Easy peasy. And we plug and chug. 2 out of 4 go here. 2 out of 4 go here. That's 0.5, 0.5. You square that, you get 0.25, 0.25. Awesome. And then you subtract that off, and you get a Gini of 0.5. So this tells you something really, really cool about the Gini calculation. You know that awesomeness ensues when the Gini is equal to 0. And you also know that it's maximized at 0.5. 0.5 implies the greatest level of impurity in the mathematical calculation because we know in the binary classification case that this is the worst case scenario, 50-50 split. So this is awesome. Now, I won't bother you with the math for the last 2 buckets. We'll just go ahead and throw those out there. And you can see here that the Gini is 0.375 and 0.375. And that's exactly what you would expect because what we know is these are not quite pure, but they're not also totally impure either. So they should have a value greater than 0, but also less than 0.5. And that's exactly what we have. And that is the basics of Gini. It's a very simple mathematical calculation. However, it's extremely powerful when the computer applies that calculation over and over and over and over and over again to find the best splits in your data. Later on in this lesson, you're going to see what I mean as we actually build up a real tree using the calculations at each step of the way, and you'll realize that each individual calculation is quite simple. It's just that the computer just does a whole bunch of them really, really fast, and it just looks like magic.